Welcome, and thanks so much for joining us for this episode. We're going to be getting more into some network topologies in this episode, as well as traffic flows. So we've got a couple of different diagrams here we're going to take a look at, and they are quite fun. There are a lot of shapes involved, and I do enjoy shapes. So Wes, where do you want to start today?
I think what we would do is just maybe start with topology, just the discussion on what a topology is before we talk about the types of topology. And it's interesting, Sophia, because, from a physical and a logical standpoint, there are different topologies, not just the how they're structurally arranged. Let's go ahead and define what a physical topology is and the difference between that and a logical topology. So a physical topology is really about the schematic, the physical layout of your network. What is the relationship of the nodes to maybe a connectivity devices? Remember, we talked about our endpoints and we have redistribution points. Well, how are those endpoints, the servers and PCs, laptops, tablets, you name it today, a lot of endpoints out there. How are they arranged within and compared to the redistribution points? Like for instance, a switch, right? How do we have it connected in a star pattern, right? What kind of cables are we using? Are we using 10G cables? Are we using Cat cables? Are we using Cat 6, Cat 7? Or are we using old cables, right? Those are the physical makeup of your network and all of the connections and the nodes relationships really to the connectivity devices. But we're not going to go to the actual topologies yet, but let's say that I've got a star topology. I just want you to think of a centralized nexus, right? And you got some spokes, and then you've got those spoke devices, right? So you got a star, right? It might be a physical star pattern, right? Cables laid out to a central connectivity device, but that connectivity device might do polling. Right? Well, in the older days, it would do polling, and it might ask every device individually so the data starts to look like it's flowing in a ring, even though physically it's set up like a star. So I want you to know that the logical topology is how the data moves across that network, and it's not contingent on the physical layout. And I'll show you a little bit more about that. But it is important to understand what topology is. We talk physical topology, the structural layout of the network and the nodes and the cables and the relationships to their connectivity devices. Logical topology, that's the data path.
Okay, so now that we are familiar with what a topology actually is or what that means, we do have a couple we want to go through. I know you mentioned star, we've got ring, we've got bus. Where do you want to start?
Sure, let's go back. Let's get in our DeLorean and let's go 88.5 miles an hour and go way back in time. So we're going to go back to one of the earliest network models that we were using, and it's this one right here. It's called bus. All right, now bus topology, essentially, you might think of it as a linear topology. We really don't call it a linear topology, but that's how it's arranged in a linear fashion. And what you would have is a centralized backbone cable. In the early days, it would be the 10-base-2 and 10-base-T, thin net and thick net, right? And these devices on the ends of this centralized linear cable would have these terminators, not the governor, but they would have resistors. And what that would do is you would terminate the ends of the cable to prevent signal reflection, right? Essentially, it's a resistor that absorbs the signal rather than it meeting an abrupt change in impedance and bouncing back to its source. Now, if you removed those resistors of that termination, the whole entire network would fail. So it wasn't very scalable. Another thing, too, is that when these networks were implemented, all we were using was what was known as carrier sense multiple access over coaxial media. That was actually the precursor to what would later become Ethernet. It was actually originally just coaxial media that we were sending collision detection, carrier sense multiple access collision detection. So what does that translate to? I know there's a lot of jargon here. What that means is that as I add computers to this bus, right? What we're going to do is we're going to add more contention on this network, because what happens is in these old bus networks, when this computer would send information onto the wire, it'd go to everybody. And when this computer here would send communications onto the wire, it'd go to everybody, right? Well, you can probably imagine that as we start adding more computers to this network, we start getting a lot more contention. And I'm just dragging these out here to kind of show you, because now we got a bunch of computers all contending for the same media. So it wasn't really scalable. Even some of the larger scales, I think, didn't even go past 500 users, right? And that seems like a lot, and it certainly was in those days. But today we have thousands. But you could have 1,000 people in these big businesses. So scalable models that you have, Not very scalable, and due to the fact that it doesn't have any fault tolerance, right? A break in the cable, guess what? Whole network's down. Well, it doesn't matter if the cable's down, if the computer goes down, guess what? Whole network goes down. Pull the resistor off the end of the terminator, essentially the termination off the end of the cable, guess what? Whole network goes down, right? So you start to see a pattern, and that's why these kind of got phased out, because they weren't very scalable in large networks, and as we needed to grow, we needed to go farther. Now, around the same time, we had competing technologies. This goes back to the days of the 802 body from the IEEE. They met in 1980, February, the second month of 1980. It's how the 802 term came about. And we had all different kinds of companies that joined that committee. Microsoft, IBM, DEC, which I don't know. They might have been Compaq at that time. But anyways, Digital Equipment Corporation, all these major companies, Cisco, all of them, right? Well, guess what? A little company named IBM, not so little, put all of their money into something known as token ring. We would later have a standardization called token ring, but then there would be the IBM token ring that would be proprietary. These were deterministic media. They were not the contention-based media of Ethernet. And what that means is I have this abstractly right here looking like a ring. You would have a connectivity device right in the middle of this. And what it would do is it would pull the devices, well, polling came a little bit later. They would have what's known as a token. It was a special set of bits that could be captured by a device saying, hey, I've got information to send. And that information would be sent back out onto the wire in a unidirectional pattern to the next one downstream neighbor. All right, well, there's a problem with this type of topology. If that downstream neighbor went offline, guess what? The whole network went offline. And that was a problem in those days. It didn't have a lot of fault tolerance. Now, I say that, but let me say this. They did find a way later on to make it a little bit more fault tolerant in the fact that the connectivity devices would go to send a token to a device that wouldn't respond, and it would reverse the order of the token, right? So it would go back the other way, right? They could keep doing that until that come back online, but that's really just kind of a stopgap, right? Now, you don't really see these anymore, almost none. There was another one that they tried to implement, and that did implement this ring topology, and that was something known as FDDI. I just like saying it. Fiber Distributed Data Interface, FDDI. We called it FDDI. All right. And the Fiber Distributed Data Interface for the time, very expensive, but very, very fast, very fast. There's not many of these networks left. If they are, they're pretty much isolated networks, very specialized people that are trying to get their return on investments. Maybe some schools might have it, maybe transportation systems, but these have been phased out. Now, there is one place you still see ring networks, WAN technologies, SONET. Synchronous optical networking, SONET, that's what they call it here in the States. If you're in the European nations, it's SDN, it's synchronous digital hierarchy, same standard, different parts of the globe. This is a dual ring. Oh, and by the way, FDDI was a dual ring topology too, which was really good. And so when I mentioned that, let me go ahead and just say it would have been more like a dual ring topology. So what could happen is you could aggregate both of those FDDI rings, and you could get I think 200 megs, and that was a lot in the day. Or what they would do is they would use that backup ring for exactly that, backup and control data, right? We still see dual ring topologies in the synchronous digital networking, synchronous digital hierarchy in Europe and SONET here in the States. And those are fiber optic communications. If you have ever heard of OC 192 or your different optical carriers, those OC are carrier standards for synchronous SONET communication. So we do see these still, but not in land environment. Not land? How about LAN environments? They're all on LAN. They're bounded media. So that's the ring topology there, Sophia. Now, the one, because of the lack of fault tolerance, right, to the bus networks and the ring networks, FDDI was great, but it's astronomically expensive in the day, right? Fiber optics back in those days, $1,500 a port. We have ports right now in our server closet here that have 100 fiber optic ports. They're nowhere near that. They were very expensive. Can you imagine that? $1,500 and you got 10 of them? Yeah, you're $15,000, and hundreds of thousands of dollars. So because of that, the expense, because of the lack of fault tolerance, this became the most popular and still is the most popular networking topology in modern networks. It is the star topology. The star topology is exactly what it sounds like. You're a smart crew out there. We've got a nexus device, the centralized connectivity device, otherwise known as our redistribution point. Our endpoints are connected to that in a star topology. Now, why is this beneficial? Let's go ahead and talk about some of the links. All right, well, guess what? Computer goes offline. That isolates that one computer. All the other computers that are connected to the switch operate like it's business as usual. All right, so that's the computer. Well, what happens if the link goes down? You just isolate that one computer. So that's one of the reasons that this became a very popular type of network topology, because it would isolate only the system that was having the issue and not bring that one system down and, chew down the whole network, right? So that's the star topology, right? You have a central connectivity device and you have the devices arranged in a star pattern. Now, I want to take a second, if I could, Sophia, and I want to stop right here because a ring topology actually looks like this. You're connected to a connectivity device. But what would happen was, instead of me saying like switches do, I could say, okay, this computer wants to send information to this computer, forward it to the switch. Switch got a MAC table, knows exactly where it goes, right? In these earlier connectivity devices, what they would do is they would pull this device and say, hey, you have any information to send? No? Okay. Do you have any information to send? Oh, you do. Okay, well, go ahead and send it to this person, then send it to this person, and then send it to this person. So I want you to see here that when we talk about that, even though this is a physical star topology, which is really what token ring would have been, it operated in a ring logical topology. It is the connection device that is actually saying, computer one, do you have something? Right up here at the top. Look at what we're doing. We're going in a circle here, right? 1, 2, 3, all in a ring, right? That's the device, the connectivity device that's doing that polling. There's pros and cons. Deterministic media, right? Why would you want to use something that is so contention-based that you could have collisions? Because it's cheap. There's not a lot of logic. There is logic. Don't get me wrong. Switches are very expensive, but compared to deterministic media, they have to have a lot more logic built into them. Why? Because they have to do that communication. I'm going to poll you. Do you have information? Oh, you do. Well, here, let me go ahead and pass that to you. But, oh, wait, that node's down. Let's reroute the whole entire community. That's a lot of extra stuff, so it was very, very expensive. So this ended up becoming the topology that really kind of won out. I want to talk about one that's more of a logical topology today, and you don't really see it too much in physical, in a physical topology, and that's a tree topology. The tree topology, you have these tiers, right? And typically you used to have a formula, and I can't remember the formula. The formula said for however many second level tiers you have the same amount of third level tiers for each node. So if you'll notice here, I've got, starting at the hierarchy, but then I've got 3 second tier nodes. Well, that means each of these nodes must have 3 nodes. And then, yes, if we go a little bit farther, then down here, this node would have 3 nodes, and I'm not going to keep convoluting this, but that's how that formula would be. But we don't really see this in physical implementation. We see it in logical implementation. Let me tell you where that is. DNS. The domain name system. We have the root hints that are the highest part of the hierarchy. We have the top level domain controllers that are just under them, and we have second level domain controllers under them, and finally we have the businesses that own their own domain controllers under them. It is a tree topology, and it does flow from the root down to the top level domains and down to the second level domains when you're doing name resolution. So that's an example of where the physical topology and the logical topology do not necessarily match.
My only criticism so far is that double ring that you showed us, I feel like they should have called that a donut, but they didn't. So that's my only criticism, but I guess it doesn't matter because it's not really around anymore. So that tree one you said is not one you'd see very often. What about this one next to it? Everything's connected and crossed over and convoluted.
This is one you will not see in a wired network. I do it just for visualization purposes, and this is what's called the mesh network. So the mesh network is one that's not really implemented in wired connections, with a caveat, all right? A mesh network is a network in which every node has a connection to every other node within the network, all right? It is almost next to impossible to do within a wired connection because the exponential connection increases every time you add a single node. So where do you actually see this? Wireless. if I have a wireless ad hoc infrastructure mode, right? You have infrastructure mode where you're going through an access point. You have ad hoc mode where every other wireless laptop can talk to every other wireless laptop without going through an access point. That is a wireless ad hoc or mesh network. Let me show you where you see this as well. In WAN environments. WAN environments use mesh topologies when they don't want a portion of the network to go dark when a router goes down. So if you were to replace every one of these with routers, you would see WAN technologies that are being used as mesh networks. Now, Anthony pointed something out. Anthony Sequeira, he's our resident Cisco just expert. You know, he mentioned, also remember, so thank you, Anthony. Remember the partial net mesh, too. I'm just going to take some of these connections out here, and I'm not going to delete all the connections. That would be a partial mesh, right? Or something like this, where maybe you don't have all of the connections out here. You don't have a full mesh, right? So in one portion of the mesh isn't connected to every other node. That's a partial mesh. So I want you to know that you still see these in WAN environments where you have ISPs that have multiple backbone routers in a mesh environment with connections to other routers. So if one of them goes dark, we don't go offline. Another place that you would see these mesh networks is in like the old frame relay networks. The frame relay network is kind of like a cloud base where you had this logical identifier on one side and a logical identifier on the other side. It really didn't map to anything physical within the frame relay network because it was a mesh network that was abstracted and controlled through the ISP. You only seen the identifiers on the end, right? So that's the mesh network. And these are some of those major topologies, you know, that we really need to talk about.
As we get further into this document, there are some diagrams here that look to me like Star Wars ships.
Yes.
So we have Star of Stars, Ring of Stars. Are these things we'll see pretty often?
Not really. Okay, so you're going to hear the term hybrid topology. What is a hybrid topology? Take any of the ones that we've given you and blend two or more. You need at least two, right? Or it's not a hybrid, it's just the model. All right. We don't set out on purpose to set these this way, right? Let me give you an example, right? Mergers, right? We have one company that has one network model and they've been using it. We have another company that comes in and they merge and they're using another networking model. Well, now we have one company that has two different networking models, so collectively they have what's known as a hybrid model. Or an acquisition. You see it in M&A. We don't set out to design a convoluted network. You shouldn't. If not, you should probably try a different industry. But we don't set these in play at start. So let me give you an example. Now, this one you might actually see a star of stars. Because if I was to replace these with just network IP addresses, then we could potentially have a router that is routing information into these, like for instance, autonomous systems that have star networks behind them, right? But this is what's an example, like for instance, a star of stars, right? We have a central main connectivity device, maybe a core backbone router, and it's connected to sub-routers within a star pattern. It's a star of stars. These are just a couple of examples. You can mix a lot of them, a star ring pattern, right? What I could do is I could have stars, actually, I have a ring of stars, right? So now I have three star patterns, but the connectivity devices like Sonnet, the WAN environment, would be the ring. All right, again, we don't set out for these. This is a ring of stars, and that was the whole Ringo star. I love it. That's how I'm going to tell people to remember it. But you have bus star patterns, right? You know, we don't try to set out for these. I just wanted you to know what a hybrid is in case, you know, maybe they ask you. Just remember it's a blending of two or more of the network topologies that we've talked about.
Now, we also mentioned at the beginning of the episode that we were going to get a little bit into traffic flow as well. And I understand there's traffic going into the firewall and then there's traffic that happens behind the firewall. So what's the difference?
Sure. Perfect. So let's go ahead. Let me show you. Let's start with north to south. All right. When we talk about north to south, traditionally, from a security standpoint, really, the traffic flows are still the same, but they haven't really become we haven't really focused on them as much since this term zero trust came into play. North to south traffic is the traffic that comes from, let's face it, an external network that you don't own into your network. It's typically the internet, right? But whoever's past that, you don't own that network. It'd be an ISP. That's the north to south traffic. In fact, Sophia, you mentioned the firewall. I really like that. What comes from the internal or an external network through your firewall into your network? That's a great way to put it. That's north to south traffic. Now, you understand the term lateral movement, right? But
Right.
from a security standpoint, what does lateral movement mean to you? I'm going to throw a question at you.
Sure. So, from what I remember, if you've got access to a network and you're able to stay on the same level, maybe my job, my permissions are the same as yours, but maybe you're in a different department, and I can jump from one profile to the other. That's lateral. And if I were to move up, that's not lateral. If I were to get into like my boss's position, that would not be lateral movement. Is that about right?
Yeah. How about a pivot? What is a pivot?
Oh, gosh.
All right. So a pivot is where you have compromised a system and now you're going to pivot laterally somewhere else within the system.
Makes sense.
All of that, the reason I say that is because maybe you haven't heard it in a network and communication standpoint, but from a security standpoint, that's internal communications inside of your network, right? Oops, and I'll get it there eventually. That's the east to west traffic. And I'm not going to bring this up too much because these auto adjustments will drive me crazy. Your east to west traffic is exactly like Sophia said, right? Your lateral, once I'm here, right, and I communicate with a station in here, well, that's east to west. That's inside the perimeter of your network, right? It is important to understand traffic flows, right? And it's not only important to know traffic flows just from a basic networking standpoint, but also from a security standpoint. I'm going to just briefly mention something called zero trust because you will start to hear more of it. The reason this started to become so important, right, is because in today's day and age, we always assume breach. We always verify and re-verify. We never trust, right? That's zero trust. We don't trust anybody. And when I authenticate you, I don't care if you're an employee, I'm going to authenticate you again, and I'm going to keep authenticating you. Well, we do that because traditionally we were only worried about protecting our north to south traffic, and we can do that through firewalls and IDSs, IDS, IPSs, right? But then once somebody got into the network, they didn't have to work quite as hard because there was an implicit trust. It was implied that once you had authenticated and you're in the network, you should have access. Well, that is not the case and hasn't been the case for a very long time. That's where the east to west traffic protection came in. Now we not only protect the north to south traffic flows, we also protect those traffic flows inside of our networks.
Absolutely. Like you said, zero trust, better safe than sorry.
That's right. Just because I think people are after me doesn't mean they're not.
Right, exactly. Just because you're paranoid doesn't mean they're not watching you.
That's right.
So we also have a couple more things here in this document, a couple of different network models. Can we walk through those real quick?
Sure, and I didn't really put this in the title, but it is important because network models and network topologies, they are close, but not really the same. I'm going to go ahead and I'm going to talk about three here. So let me go ahead and just breeze by them real quick. Take your motion sickness pills. So we got centralized, we got client server, and we got peer-to-peer. I'm going to come back. Let me not drive our poor director crazy. Let's just focus in on one of them. We'll come back to the other. Centralized was one of the very earliest models. Now, networking models, all right, a little bit different, all right. Who controls the communications within the network, right? Well, in the early days, we had mainframes that would be connected to terminals. Dumb terminals. The terminal was called a dumb terminal because it just had a keyboard. And it didn't even have a mouse in those days. It had a keyboard and a freaking monitor, and that was it. Because the centralized mainframe, I'm calling it a host computer, and I got to be careful with that today. The host computer controlled all the processing, controlled all the network communication, and controlled all of the data storage. That's why it's called a centralized networking model. Well, you might see that, that's good for very large corporations that can really afford a $2 to $3 million mainframe. Well, what about the smaller companies? Well, this wasn't really something that smaller companies could have. So one of the things that we would find, so how about this? If we lost connection to the mainframe, guess what? That terminal went dark. You no longer could get any work done, right? So it wasn't very, what happens with the host? Host goes offline. All the terminals go down, right? So it's not very, as far as fault tolerance goes, there was a better way to do it. And they came up with the most common model that we have today, and that's the client-server model. All right, in the host model, the centralized model, that host controls everything. In the client-server model, you have clients. Clients is just an operating system that is requesting a service. Hey, I need a file out there. In my case, I said, hey, I need a resource. Could be a file, could be a website, could be any one number of things. But then the server is the one that is playing a role out there, listening out and saying, hey, yeah, you need that file? I'm an FTP server over here. You can find that file over here. So the client-server relationship, what that means is clients are operating systems requesting servers, and servers are those operating systems providing the services that our clients need to perform or need to use. Now, how does this model benefit us versus the old model? Well, your clients are self-sufficient computers. They do their own processing, their own storage, they control their own network communications. So if I lose access to the server, I'm still productive. I could still work. I have a self-sufficient computer, and that's why this has been more of a popular model, especially in an enterprise. Last one, but not least, if you've been around a Windows environment, Windows calls this a workstation, a work group, not a workstation, a work group. All right. The industry as a collectively knows it as a peer-to-peer model. Now, what's the difference between the client-server model and the peer-to-peer? Well, just really only one thing. What makes them peers is that in a peer-to-peer group, a computer can act at sometimes like a server, providing a service, but then at other times it can act as a client requesting a service. All right. So what we have as far as peers is that they are equal in the client and the server mentality. Let me give you an example. One computer can be offering a print service and have a printer connected to it, where another peer says, hey, I need to print something. Come on over here. I'm acting like a print server right now, and I can provide you with that service. That same computer is now storing a file, and it says to the rest of the peers, I have that file you need. It is now acting like a server. So the roles are basically every computer can act as a server and a client. That's what makes them peers. These are the three networking models that I would be aware of, and some of the other topologies and some of the considerations when it comes to whether you might be taking an exam or maybe you were just trying to move up the help desk ladder. If you know these and you can identify their strengths and weaknesses, it can help you tremendously.
These different network models and topologies and traffic flow, they're all, separate topics, but they all kind of blend together. They all kind of have to do with each other. So it's good to talk about them collectively in one episode and talk about how they relate. Thank you for walking us through all this, Wes. I really did like those diagrams. They were fun. It was like looking at Star Wars battleships. And thank you for joining us for this episode, and we'll see you next time.